الحضور الكرام، السيدات والسادة، أهلا ومرحبا بكم في محاضرة أخرى يقدمها لكم الفرع الطلابي لجمعية مهندسي النفط العالمية الخاص بجامعة البصرة للنفط والغاز. معكم فاطمة عزيز هادي، طالبة مرحلة رابعة ومسؤولة الأنشطة الاجتماعية للشابتر. سأكون معكم كمودريتر خلال هذا السيشن. نستكمل معكم اليوم المحاضرة الثانية من الكورس، والتي نقدمها لكم تحت عنوان Application of Artificial Neural Network in Oil and Gas. محاضرنا لهذا اليوم هو الدكتور أحمد إبراهيم. نقدم لكم البعض من خبرات المحاضر. أستاذ مساعد في جامعة الملك فهد
Assalamu alaikum. So it seems we lost here, so probably I'll just start. So my name, as she says, my name is Ahmed Ibrahim. I'm assistant professor at King Fahd University. It's my pleasure to be invited to this amazing speech chapter. My presentation today, inshallah, will be about application of ANN in oil and gas industry. So this is my outline. So I'm gonna start with some introduction about the machine learning. What's the different type of machine learning, like supervised and unsupervised? What is the main difference between each type? I will have some examples for the machine learning tools, like that can be applied on the oil and gas industry, and what is the application for it. Then I will go in details on the artificial neural network. We'll have some introduction about the artificial neural network, how it is started, the structure of the ANN, and I will end with how this artificial neural network got to learn from our data in order to build a model to predict the future performance. And then I will highlight some of the application of the ANN, some case studies that I did published on in different journal papers for the application of artificial neural network on petroleum industry, on the area of production engineering, reservoir engineering, and drilling engineering. So let's start. So machine learning, as we know, we have been using the machine learning for type. It is a science of getting the computer to learn without being explicitly programmed. So the typical programming mode, which is basically we write a code to like using whatever programming language to make 1 + 1 = 2. However, in the machine learning, no, we don't have to give explicitly the equation or the code in order to have the output, but we will just ask it to learn from some experience. So as I said, there is examples that we have been using all over our lives, like the photo tagging in Facebook, for example. You can, based on the photo, or even in your cell phone, you will be able to cluster the photo based on the person. Anti-spam filter and web page ranking based on the how relevantly you use the website. You will see that there is some suggestions for you to use. This, all of it is basically a machine learning tools. So learning algorithms are also used in order to customize the recommendation by any sellers like Amazon or Netflix. Based on the movies that you start to watch, it will give you some recommendation based on it. So the learning algorithms are also used to understand the human brain and the human learning in order to understand or explicitly to try to predict the future performance of a certain human. So the learning, the machine learning, there is different type of machine learning. The main classification for the machine learning is supervised or unsupervised machine learning. So there is two main categories for the machine learning. It's either supervised, where we supervise the teaching or the learning of the tool, or unsupervised machine learning, where we just put a bunch of data to the tool and ask it to learn by itself. So for more details, the supervised machine learning, it is the most common technique in the applied in the machine learning. Is basically we teach the computer on how to learn. So we teach it on how to learn. So we give it some input data and certain output data, and we ask it to learn from this input data in order to get the output data that we actually give it to it. However, in the unsupervised machine learning, we let the computer learn by itself based on a certain class or a certain classification. So supervised machine learning, it is probably the most common technique. Supervised machine learning also, we basically give the model the correct answer. So this is basically what I'm saying here. We have different input parameter x1, x2, x3, and then we give the model also the output, who is the one that we want to predict in the future. And then the model will start to learn from this one here, try to have a model, and then that give you a certain y, and try to modify or optimize the model learning by comparing the stuff that he got from here with the actual data. An example for this one here is predicting, like this is a very general example, predicting the housing prices. Okay, based on the location, based on the time of the year, based on the number of like the apartment, and so on. So based on a lot of input parameter, you can have a certain price for your house. From the oil and gas industry, we can say, let's say the prediction of the porosity, for example. The porosity is basically can be a function of many parameters, like the bulk density, can be a function of the clay concentration, it can be a function of the like maybe you measure that using the neutron porosity. So basically we give the model a certain input parameter and we ask it to get an output parameter. Okay, so this is the first type of the machine learning, which is the supervised machine learning. Another example of the machine learning, and this one here you can see all our output is basically a continuous parameter, where basically the porosity it's basically can have a values from let's say 0.1 up to let's say 0.25. The porosity can be any value in between, can be 0.11, 0.12, and so on, any continuous value. So in this case here we call it a regression problem. Another type of the problem is the classification problem, where in the classification problem we give the input, we give the model, yes, any type of inputs, x1, x2, x3, and then we ask it to have y, the output. In this case here, this y here can be like a certain class, it's a black or white, it is 1 or 0, and so on. So this one here, it is called a classification problem, where your input parameter is basically a discrete values. It's either 0 or 1, it is right or false. Okay, so you also in the classification problem, you may be able to predict 2 or more classes. So you can have, for example, predicting the lithology of your formation. The lithology of the formation can be sandstone, can be carbonate, can be clays, it can be shale, and so on. It can be anhydrite. So all of this one here is basically a class, but like you cannot say it is between sandstone and the limestone. You cannot say it like this. So basically, yes, you can have it as a percentage, but it's still a class. Okay, so this is the first part of the machine learning, which is the supervised machine learning, where you have a classification problem or regression problem. Again, another example of the classification problem. Basically, this is also a very public or very general example, where you're having different features to classify the tumor. Okay, is it good? It is like a benign or malignant. So it can be the size, it can be the age, it can be the uniformity. Again, you can see that the X, the input to your model is basically can be a continuous value. It can be the age of the patient, can be from whatever 10 years up to 60 years, anything in between. So this is a continuous value. However, the tumor can be in this class or can be in this class. So the classification problem, use this one here in order to predict which class the patient will be based on the input parameter, like the size of the tumor, the age of the patient, the uniformity of the location of it, or something like this. Okay, you can use infinite number of features to do the classification. So the number of input parameter here you can use as much as you can. And we will have some discussion about the number of inputs that you may use in your machine learning. So remember, in supervision machine learning, you have a regression problem or a classification problem, where the regression problem, basically you are predicting a continuous value of output. In the classification problem, you're predicting a discrete values. It's either right or false, 0 and 1. Okay, and both are supervised machine learning, where we basically give the model an output value. So the model will try to predict this output value and try to optimize itself by minimizing the error between the actual and the predicted values. Okay, so basically I focused on the supervised machine learning because this is basically will help in the artificial neural network. So artificial neural network is an example of the supervised machine learning. Okay, so as I said, it's basically you give the model a set of data without telling it what the output of it. And based on the clusters, based on the properties of the data, the machine learning will start to cluster it to a. Okay, so you have a certain lithology, for example, you'll not tell the machine learning that this one here is sandstone or this one here is limestone, but based on the input parameter, the machine learning will be able to detect, yes, this part here is one class, this is another class, and this is another class, but it didn't know that this one here is sandstone or limestone. It just know it is just a cluster. So this is the main difference between the supervised and the unsupervised machine learning. An example for the machine learning tool that we that have been used on the industry, and a lot of people are using it, is the artificial neural network, which is going to be our focus today. There is other machine learning like the function network, support vector machine, adaptive neural fuzzy interference system, which is the AMFIS, random forest, decision tree, gradient booster regressor. A lot of, there is multilinear regression. There is a lot of different machine learning tool that you can have it in a different language like Python or MATLAB, and you can use it based on your application or your problem. So let's start with a simple example in order to understand how the machine learning or how the artificial neural network works. So let's say we want to predict a permeability formation permeability, which is K, as a function of a certain input like the rock density, bulk density, or the porosity, the sonic velocity, and the water saturation. So we want to use this input parameter in order to measure or estimate the permeability. So this means basically we are trying to have K as a function of rho, phi, Bs, and water saturation. A very simple way of having this one here is basically the linear regression form. Linear regression form is basically a constant multiplied by your input parameter. So we can have it in a general form. It is basically AI multiplied by Xi plus B will equal to your permeability, where A is basically the weight of each input parameter. So you have the input parameters here, or the features here. It is basically the density, the porosity, the shear velocity, the water saturation. You need to have a weight from this input, and then you add some biases to it in order to have it pass by the zero. And this should give you the K value. So this is a very simple model. It is a linear regression model in order to predict the permeability as a function of 4 different input parameters. So now the question is how to find A1, A2, A3, or in this scenario here, it is A, B, C, D, and the bias, which is E. So easiest way is we have 5 points, and we solve this 5 points with 5 equations. So we have 5 equations and 5 unknowns. So we have, for example, 5 points, and try to fit it with just a straight line, okay, by solving in order to find A, B, C, D, and E. Yes, this is very accurate, but the problem is the relationship between the permeability and this parameter here is not linear. Okay, that means this one here is not acceptable. In addition, we don't have only 5 points. We're going to have a lot of points that may not fit. Okay, that is not maybe not satisfied when you do the regression based on only 5 points. So this is what I said. You basically use 5 samples to solve a 5 unknowns. So it's 5 equations and 5 unknowns. So it's basically linear regression method. You can do it with the least square method in order to find the weight of each input and the biases to the whole equation. Or it can be something like this, or you can have a nonlinear regression for based on your understanding for the problem. The problem is with this complex problems that maybe there is no direct physics between the output and the input. So for example, the shear velocity here, there is no straightforward relationship or physics relationship between the permeability and the shear velocity that you can have it in analytical form. Similarly applied to the porosity or the density. Okay, yes, there is some, like we can say, yeah, when the porosity increases, the permeability increases, but it's not always. Sometimes you see that this is the data point that you have between the permeability and the porosity. You will see that at the same porosity, you may have a permeability here and you may have a permeability here. Okay, so this doesn't mean that there is always a straightforward relationship between the permeability and the porosity. So when the physics is lost, when you don't know where no clue where we go, we don't know any shape of the equation. You don't know it is a linear relationship. You don't know it is a polynomial. You don't know it is logarithmic. You don't know you need to use an exponential relationship. You don't know the shape of the equation. So in this case here, what you're gonna do, you use the artificial neural network. So artificial neural network, basically, you don't need, for any of the machine learning, you don't need to know the physics. For sure, you need to have a sense of the relationship field between the properties you need from your understanding for your problem. So as a petroleum engineering, the relationship between the water saturation, for example, and the permeability. If you are talking about the effective water saturation, okay, probably when the water saturation increase, I know that the permeability of the water should increase. So this is based on your understanding from the your problem. The same for the density. Density is the bulk volume. Bulk volume, like something like this one here, it represents the whole density of your rock. So okay, if your density here is high, that means it's dense rock. That means the pore size or the porosity is very small. That means probably the permeability will be low. So you have a general feeling of the relationship between the parameters, but you don't know the exact shape of the relationship. So here we have the neural network, where the neural network use available data set, try to learn in order to have a model that can be used to predict the output from your input. So the artificial neural network is basically a mathematical model for learning inspired by the biological neural network that we have in our brains. So basically in our brain, we have neuron like this one here that take all the inputs, okay, from basically a certain knowledge from any of your sensing, and then try to translate this one here with a certain relationship in order to have a conclusion and output. Similarly, this is the way of the neural network, how it works. So basically, it has some input parameters like x1, x2, x3, and then with some, this neuron here start to have some function, activation function or transfer function that give some nonlinearity for this input here in order to transfer it to the output parameters. Okay, so this is the output. This is how the the neural network work, we can model a single neural network by basically mathematically loosely by using the perception as shown here. So basically we use the input, a certain weight from the input. We have a transfer function or activation function where we can get your output out of it. The neural network is very, very common technique. That's very famous machine learning technique. It has a lot of applications in oil industry and other industries. Okay, so it's allow the machine learning or the neural network. It's allow learning the network by updating the parameter of your artificial neural network. So basically, the neural network consists of a network of neurons. So here, I just showed you just one neuron. Just one neuron, similar to what we have in our brain, is basically takes the inputs from your senses, for example, try to make some transformation on it, take a weight based on the importance of each input, and then come out with the output. In the neural network, actually, we have a lot of neurons, okay, which called perceptions. And this perceptrons here, which is basically a one layer, for example, it can be one layer network or can be multi-layer network. So typically we have an input layer, which is layer number 0, and we have the last layer, which is the output. And in between, we have a hidden layer where we have the learning process. It can be a hidden layer, as I said, or it can be more than one layer. And each layer, it has one neuron. Each layer, it has one neuron. So basically, the input go to the first layer for each neuron, go to each neuron in the hidden layer with a certain weight from each of this input, x1, x2, x3. And then there is some transformation function or activation function here, where it adds some activation, where it adds nonlinearity to the relationship. And then the output from this neuron here also go to the next neurons in the second layer, and so on, so on, so with a certain weight, and then with a certain transferring function. And at the end, from this neurons, the last one, it go to our output here based on the x1, x2, and x3. So the activation function that we are talking about here, it's basically, it defines the relationship between your input and your output. So the activation function can divide it into two relationship or two types, sorry, non-differentiable activation function or differentiable activation function. So non-differentiable activation function here is basically a hard limit transfer function. We call it hard limit transfer function. It is basically, it's a function where based on a certain threshold or a certain criteria, it gives you 1 or 0. Okay, anyone remember from this one here, 1 or 0, right or false? It's basically classification. So it is, as I said, it is a hard limit transfer function, a hard limit, which is basically the threshold at a certain value of x, for example. If this x here is less than this threshold here, your output is basically 1. If it's, or is basically 0. If it's higher than this one here, it's basically 1. So it is 1 or 0. So the hard limit transfer function that's always used on case of classification problem. There is other transfer function or activation function, which in case of the soft layers, there is a lot of different transfer function which gives a non-linear relationship between the input and the output. It can be log sig function, and we will have an example of the log sig, tan sig. I'll show you also what is the equation for the log sig and the tan sig. This is soft plus. There is a lot of different functions here, and also it will depend on the model that you're using, the programming language that you're using. There's like Python, there is MATLAB. In the MATLAB, there is specific functions that's built in the model, or you may need to build your own functions, the same in Python. Okay, so this is the activation function. Activation function, basically, it is a transfer function from the input to the output in order to give it the non-linearity based on the relationship between the input and the output. So it helps the neural network to learn the complex data, complex relationship between the input and the output. So this is for the structure of the neural network. We said the structure of the neural network is it's basically a set of layers. Within these layers, it has the neurons, and these neurons here, it take or learn from the input by a certain weights and biases. So how this network start to learn, how it learn from the your data. As I said, neural network, it is a supervised machine learning. So basically, supervised machine learning, that means I gave it the input x1, x2, and so on. And at the end, I have my output, y. Okay, so let's say our output, basically, it is g of x. Okay, so this is our output. So the overall of the model training, when we train the neural network, is to come up with a model, a certain model that give us an output based on the x1 and x2 is very close to the actual output parameter or output value, which is gx. So this is the overall goal of the training process. So to model the neural network, we need to derive a parameters of the neural network, which is basically the weights and the biases. So as I said here, we take some weights from the input parameter in addition to a biases that we input to our machine learning in order to come up with the output value. So what we are looking for is we try to find the weight and the biases in addition to, so this is your biases here, in addition to the transfer function that give us the base value of your output. Okay, so this is the one that's coming from the model, and this is the reality, the g of x. What we are looking for, we are looking to minimize the error between the, we are looking for the weight and the biases that minimize or produce the desired output from the training input. Once we have the model trained on a certain machine in a certain data set, we can use it later on to predict the future data. To determine how good our estimate is, so we trained our result. As I said, we assumed a certain value for the weight and biases. We put it in our model here. We take a certain weight from the input parameter x1, x2, x3, and then we come out with a certain output y. In order to know how good our estimate is, what we're gonna do is we basically calculate what we call the divergence or the error. So the divergence function, it basically represents an error function between the actual output and the estimated output. It can be a different error, like root mean square error, the combination between the root mean square error and the absolute mean error, and so on. But how we reduce this one here? Okay, so for example, this is just like more general network here, where you have your network consists of the input and the output layer, in addition to 3 hidden layers. And then when the in order to learn how this neuron here learn, is basically take the input x1, x2, x3, x4, okay, from layer number 0 with a certain weight, So we take it with a certain weight, which is basically this one here, in order to come up with the value of that go to the neurons here. So for example, this is x1, I'll take 0.5 out of x1, and I will take 0.7 out of x2. I will take 0.3 out of x3. Okay, so 0.5 multiplied by x1, this is basically the value of y that will go to your neuron here. And then based on this neuron here, with some transfer function, it will transfer it again as if it is an input for the next neuron, and so until you reach out to the last output. Minimize the error. So
العفو أستاذ، بس الصوت فصل.
العفو أستاذ أحمد، ماكو صوت.
دكتور أحمد، الصوت بعده فاصل عندنا. تمام أستاذ أحمد، إذا تقدر تخرج من الزوم بعدها ترجع تدخل مرة ثانية.
السلام عليكم.
وعليكم السلام، أهلا أستاذ.
Okay, apologies for the something wrong with my mic. So let me.
تمام، مو مشكلة.
Okay, let me.
سكرين همين ما مشير عدنا، فإذا تقدر ترجع تسوي شير سكرين.
Okay, I'm doing it right now.
Okay, thank you.
So we disabled me from sharing. Can you please allow me? I still cannot share.
Mr. Ahmed, do you hear me?
Yes, I can hear you, but I'm not able to share because the host disabled me from sharing my screen. So I sent here the presentation. I'm waiting for it to share.
Or you can't share your screen now?
No, I cannot. So should
Okay.
I can send the presentation to you.
Okay. I'm sorry about this problem. So now we solve this problem. Sir Ahmed, you can share your screen now.
Okay, let me try.
Okay, try.
Yes, I can. Okay,
So we saw about this problem. So we appreciate your waiting.
that's fine. So let's continue. So as I said, in order to minimize the error between the neural network estimate and the actual one, we use what we call the gradient descent algorithm, which is basically based on calculating the differential or the derivative of the error with respect to the weight. So as I said, as I was saying, if this is the weight for a certain interval from weight equal to, let's say, 0.1 up to 10, for example, and we have a different values for the error. So the optimum weight is basically, it is the weight that gave us the lowest value. So in order to go here, what we need to do based on this technique here, we need to estimate the derivative of the error with respect to the aspect, which is basically the slope here or the dy by delta x, the derivative of your error. If the slope is negative, basically if you are somewhere here and your slope is negative, your derivative is negative, that means you need to increase the weight of this parameter. So if the weight of the first parameter x1, for example, if the first weight here, first estimate or the first value of the weight is here, that means the derivative is negative value. That means I need to go to a higher weight, put more weight for this x in order to optimize the weight value, and so on. The other scenario is if the slope is positive, which is something like this, that means your weight value, it is on the right of the optimum value. It is higher than the optimum value. That means I need to decrease the value of the weight. So this is just another explaining for it. It's basically iterative method. We start with any just a start point, regardless if the weight is, and then based on the derivative of the loss or the error with respect to the weight, we can go to the left or right. If it is positive, we go to the left. If it is negative, we go to the right until we reach to the optimum value. So that means how we jump, how much we jump here. So the jump here is basically what we call the learning rate. So this is the first estimate, or this is the first estimate. This is the second one. If this one here is higher than a certain error, that means it's not acceptable yet. We did not reach it to the optimum value. So what we're gonna do, the first weight is the second weight that we are looking for. It's gonna be equal to the initial estimate. So this is the initial x, and then minus a certain learning rate multiplied by the derivative. Okay, so this is our derivative. If this one here is negative, that means we're gonna add a value to the x. So we will jump to the right. And the other way around, if this is the value of the weight initially, and we have the derivative as a positive value, you will see your value, the second estimate for the weight will basically gonna be the initial weight, which is this one here, minus, so this one here, it is minus value, a certain rate, learning rate multiplied by the f of x, the derivative of x. That means you will jump to the left. Okay, so the learning rate here is very, very important. It reflects the step size, how you jump with your weight estimate each time you do the iteration. So this is just a quick example for the gradient descent. If you have a certain function f of x1, x2, x3, in our cases here, it is a weight 1, weight 2, weight 3. It's something like this. If you want to get the optimum value of x1 and x2 and x3 of this one here, you basically calculate this derivative, and then you need to jump for the weight. If the start weight value it is 1, 1, 1, what gonna be the next jump what is the next values of the weights for each features, it gonna be estimated using this formula. The new weight is equal to the old weight minus a certain learning rate multiplied by the derivative. So that's based on this one here. You can get the new values of the weight x1, x2, x3, and so on. So you will use this new weights and repeat, check the error. If the error is less than a certain tolerance, we reach to the optimal value. If not, we need to repeat this one here to have a new weight. So the step size, which is, as I said, the learning rate, is very, very important. So if your problem it is something like this and it has concave shape, you will have just a single optimum value. But if it is very like this, you're gonna have a local minimum. And in this case here, the learning rate is very, very important to define carefully. So if you select your learning rate or your step size here, it is less than the optimum. You were here, and you will less, your step size is very small comparing to the distance from here to the optimum. So what you're gonna do is you're gonna jump the first iteration. You need another iteration, and so until you reach it to the optimum. Yes, this one here is very safe. You will reach it to your optimum, but it will take a long time. The second scenario is where your jump or your step size is equal to from here to here. It is optimum. You will take you directly to the optimum, and this one here is so difficult, we're not able to have it. Basically, this one here, it will happen if you know the solution, which is will never happen. The third scenario is if your optimum, if your step size here is higher than the optimum, okay, and it's between the optimum and double the optimum values. That means, okay, your initial step here, your first jump will take you to the next step, and then if you are lucky, you'll go up and down, up and down, up and down until you reach to the optimum. The last scenario, if your step size is very big, it will basically the other way around. It will take you the other way around. So you are here, it is higher than 2 of the optimum. That means it will take you higher in the other side, and so it will take you away from your optimum and you will never converge. Okay, so this is the importance of the step size, which we call it the learning rate. This one here is one of the parameters that you need to optimize in the artificial neural network model. So just to summarize, the artificial neural network is basically consists of input layer, output layer. The input layer here, you have a control on it. You need to do some statistical analysis. You need to do some transformation on it. And then you have hidden layers. The hidden layers here consist of different neurons. This neurons here is basically what it's learned, and it's controlled by the weight and the biases. And you also have some control in the weight and the bias. You need to optimize this one. So let's have an example of how to develop a artificial neural network model. So any machine learning development model go through different stages. The first one is the data analysis, which based on your data, you need to know your data. Start to develop your model. Develop your model meaning you optimize it, try to choose your transferring function. You try to use the number of hidden layer. You need to choose as a number of neurons. Develop the model by training and testing. And at the end, validate the model with unseen data in order to make sure that this model here is not biased and it can be used to predict another data set. So for the first step, which is the data analysis, basically, as I said, the statistical analysis, which you need to define the for each parameter x1, x2, x3, you need to define what is the mean, what is the median, what is the minimum value, what is the range of your data. Your positive, for example, is vary from 0.1 to 0.5. Your density vary from 1 to 2. Your gamma ray vary from 1 to 100. So you will see that each one has its own range. It has its own variance. It has also its own shape of distribution. It is normal distribution or a log normal distribution. This means you may need to do some analysis, some pre-analysis or pre-processing for your input data. A quick example here. Basically, I want to predict the permeability as a function of the porosity, the resistivity, the gamma ray, and this is the density. Okay, I want to predict the permeability out of this one here, for example. If you look to this parameter here, the porosity is basically vary from 0.02 to 2, resistivity from 10 to 1000, gamma ray from 100 to 300, and I want to have my permeability from 0.1 to 50. Okay, so you can see that all of my features, which is x1, x2, x3, has a different range. So when you use your machine learning model and try to estimate the weight, oh, a small change in the porosity from 0.1 to 0.15 actually have a huge impact on the permeability, comparing to if you change the resistivity from 10 to 10 point, what happened here? It is just a change on 0.05. It's to 10.05. So as if this one here has no impact. Example for this one here, it is like when you mixing a fruit juice, like an apple and strawberry, for example. A strawberry is very small, the apple is big. So if you put one from this one here and one from this way here, you will end up your fruit is basically has toward more apple. So that means you need to do some scaling. So there is different scaling techniques. So we want to avoid deceiving the importance of the parameters, and we need to reach to the converge very fast. So if you need to avoid this one here and this one here, you need to have your input parameter in the same scale. Okay, all the parameters vary between 1 and 0 to 1 or -1 to 1, based on the techniques that you're going to use in the scaling. So there is very common techniques, something like this, the normalization. There is a normalization technique, and there is other technique. The normalization technique, for example, it is a feature minus the minimum divided by the range, the maximum minus the minimum. And in this scenario, the scale of it will be vary from 0 to 1. In case of the standardization technique, it's x minus the average of your data set divided by the standard deviation. So this one here will take all your parameter to be around your mean and the standard deviation. Your mean will be basically 0, and your parameter will be very around the 0. Yes, it is not from 0 to 1. It's probably going to be from, let's say, -1, -3 to 3. So if you are talking -3 to 3 and another one, it's 0 to 1, you're still in the same scale. You're talking the same level. A quick example, this is the original data for the porosity, gamma ray, and the resistivity, for example, and your permeability. If you did normalization, what's going to happen? It will grab all your data to be between 0 and 1, but your mean will not be equal to 0. It's a different value from one scale, from one feature to another. If you did the standardization technique, it will grab all your property to be around a mean of 0, and it's just going to be within this level here. You can see it's between -2 to 2, between -3 to 2 point something, and so on. Depends on the distribution. Which one is correct? There is no rule to say which one is correct. Okay. All what you need is to run the model with your raw data.
Mr. Ahmed, do you hear me? Your share screen is stopped right now. Mr. Ahmed, you can't share your screen.
Assalamu alaikum, can you hear me?
Yes, I can hear you.
I
So you
don't know
can
what's
now
going
share your
on.
screen.
Yes. Okay, 1 second. I got disconnected again. Okay, can you
Okay.
screen now? Okay.
Okay,
So,
wait a minute. So now we can't
Oh.
see your screen. So, okay.
as I was saying, there is no actual scaling technique you're gonna use, like the normalization or the standardization. Just run your model with the raw data, see how the performance look like, scale it with the normalization technique or scale it with the standardization technique, and see which one will fit your data much better. Another also pre-processing is the data transformation based on the distribution of your data, how the data look like. Like a very common example for this one here is the permeability and the porosity. Permeability, typically it has a log normal distribution, where basically most of your properties, most of your samples, it is in the lower end, and you may have a few samples at high permeability, okay, with maybe natural fractures. So it has a weight on it. So if you look to the relationship between the porosity and the permeability, if you want to predict the permeability, which is in the orange curve from the porosity, oh, there is no relationship. I cannot detect it from here. But once you make a transformation for the permeability from the normal scale to a log normal scale, you will see that, oh, the permeability and the porosity actually aligned to each other. There is a perfect relationship between the permeability and the porosity, and you'll be able to detect it easily. So the transformation is one also of the pre-processing step that you may need to check your input parameter, your output parameter. Yeah, it is better to predict the log permeability than the permeability, or the log of the gamma ray than the gamma ray itself, because it will make your model converge faster and you will have better performance. We'll come to the last step of the model after we develop the model, is the model evaluation. How to evaluate your model? By comparing the actual versus the predicted through what we call the cross plot. If your data is aligned within the 45 degrees, that means your prediction is perfect. If it's scattered like this, that means your model may need to have some optimization by adjusting the number of neurons, the number of layers, adjusting the transferring function, adding another features like another property in order to predict the output. Or you can have a trend like this. You plot the actual and the predicted on a trend like this versus dips in case of wheel logging, for example, and you'll see how the actual versus the predicted look like. In order to quantify this one here, you may need to calculate the residual error. Residual is basically the actual minus the predicted value. See how it look like. Is it around the zero? Most of it is around the zero, or there is some point that is further away from the zero. Okay, this is from the quantification point of view. Also, the average square error, mean absolute error. So this is the absolute of the error divided by n. What is the value of it? Is it high value or is it low value? So the higher the error, this error can be absolute error or mean square error. So the absolute here or the square is basically in order to remove the sign effect. So the higher the error, the lower impact or the lower performance your model is. So that means your model is not working fine. You need to readjust your input parameter or your model parameters. So also another issue that you may see, it is underfitting problem or overfitting problem. So for example, if this is your data here and your model is here, actually your model is not able to detect any of your model here was not able to detect any of the model parameters. You will see that this is because your model is very, very simple. So that means you may need to have your model more complex or add another features to make your model more reliable. And the one in the right hand side is basically more complex. Your model is very, very complex. As a result, it basically memorized the whole data. So basically your model, it is memorizing all the data points, but it's not the general trend of your, it's not the general trend of the model. So it's not able to get the general trend of it. So let's go to the example very quick, to the example that we have for the AN in the oil industry. The first one from the production point of view, basically it's in order to predict the oil rate through the wellhead through using the choke parameters like the gas oil ratio, the pressure, the size of your choke, the oil rate, and we want to predict the oil rate. So the first step, as I said, is basically data analysis. We analyze the data by defining the minimum, maximum, mean. We need to do some transformation, and then we split the data to 40-30% based on the your data. You split your data to have it as 30-40% for the training and testing, and then run your model for the training. In this case here, the model was got a good result for the training at 1 layer with a 5 neurons. This is a very simple one, and the transfer function was we use here is 10 seg. This is the result. How we compare the result between the predicted and the actual. Actual is the right and the x-axis. And from the quantification point of view, you have R square 0.98. The absolute average error, it is 0.88. This is good. The same for the testing dataset. So this one here is the training dataset, and this one here is the testing dataset. Also from the trend, how the trend look like, trend matching, you can see that, yeah, your model, the predicted one, was able to detect most of the changes on your actual values of the flow rate with error of 1% and R square of 0.97. A good addition from the neural network also is empirical correlation. If your output, if your model basically consists of one layer, actually you can export this one here into an empirical equation. So this one here, it was 5 neurons for this parameters here. So you can see this is the parameters that I used as a transformation. I converted the gas-oil ratio to the gas-oil ratio to the power of -2. The same for this one here. For the diameter, I used log the diameter. The pressure of the distributor, I used the square root of this one here. And for the flow rate, I use log flow rate instead of just the flow rate. In this case here, the 10 seg was the transferring function, and this is the equation of it. And based on this function and the weight and the biases, actually you can have your equation to be an empirical equation like this. So you can use this equation directly without the having a machine learning to run and saving the network and rerun the artificial neural network again. No, you can use the empirical equation directly. Another example here is basically the prediction of estimated ultimate recovery for shale hydraulically fractured well in a shale reservoir. Again, we start with the statistical analysis, like scattered plot like this. It shows the relationship between the input with the output. It shows me the distribution of your input parameter, how it look like. Is it normal distribution, or you have some parameters that may be at the high end that you need to normalize for? Again, this is a statistical parameter, the mean, standard deviation, the minimum, the maximum for all my properties. Also, I have the correlation coefficient between the output parameter and the input parameter. From this one here, for example, you can see that the EUR, it's highly dependent on the initial flow rate, QI, or highly dependent on the slurries that you inject. The lateral length is very impactful on the EUR. However, like the treating pressure in this case here has very low impact on the EUR. This means you may exclude some of the parameter if you don't know it. You can just remove it in order to have more simple model. The result for it again is basically a cross plot between the predicted and the actual. As far as your data point, most of them aligned to the 45-degree line. That means your model was able to predict your result accurately. The check also quantify it using the R square, like this. And in this case here, you predict the EUR, it's 0.9, 0.93. That means your model was able to predict all the data point in case of training and testing. Again, another empirical correlation here. In this case here, it was log seg transfer function, and this is the equation for it. And using this one here, and the number of neurons was 8, based on optimize the number of neurons in order to have a better performance. It was 8 in this scenario. And this is the equation for it without the need of running the neural network again. This is always the case that we can have the model to be matched with one layer? No. Maybe if your problem is very complex, you will need to have more than one hidden layer. And in this scenario, if you have more than one hidden layer, two hidden layers, for example, this equation here will be very, very complex, and you are not able to extract it like that. The last here example is the prediction of the formation tops of lithology from the drilling parameters. Basically, you have the rate of penetration, the pressure, the torque, the weight on bit, and you can predict the lithology. So this is a classification problem. It is yellow or purple. It is sandstone or anhydrite, or is carbonate, and so on. So this is just a classification problem. This one here, it is a regression problem, and this one here as well, the one for the flow rate. However, the last one here, it is basically a classification problem. I want, this is the ROB, Q, and so on. So what is my lithology? It is sandstone or anhydrite or carbonate, and so on. Again, statistical analysis, the data here, what is the minimum, what's the maximum, and what is the correlation between your input and your output. It seems that the weight on bit has highly impact on the lithology identification, the same for the torque. And this is the result. The result in case of classification, it can be basically comparing your lithology, the actual versus the ones that you have here for the model, or basically compare with the confusion matrix. Confusion matrix is basically telling the true label versus the predicted label. So for example, here, this is a training data set. I had 1,000 or 1,006 data point was sandstone, and it was predicted as sandstone. However, in case of testing, for example, I had actually 422 of the data point were sandstone plus 2, sorry, so the number of sandstone in case of true, it was 422. But when we predicted this one here with the model, we predicted 422, and another 2 of the sandstone, we mislabeled it to be anhydrite. Okay, still it was have a good, so you can see it here. There's some point that was like misclassified as another formation using this machine learning. Okay, just to summarize what I said, basically the artificial neural network is a machine learning tool that we can use it to help us in our problem, to use it to predict a performance based on a certain data set that we learned from. And we can use it for as a supervised machine learning for a regression problem or classification problem. We need to optimize your input parameter. You need to optimize your hyperparameter, which is the model parameter, like the number of neurons, that transferring functions, number of hidden layer, in order to have a good model results. Okay, that's it. This is the end of my presentation, and I'll be happy to answer your questions, inshallah.
Thanks, Dr. Ahmed, for this very valuable lecture. So I'm really apologize about the problem and the connection at the beginning of the session. So anyone you have any question, you can drop your question on the chat box, or you can make a raising hand and ask unmute, and you can open your mic. So we have raising hand from Muhammad. So you can open your mic.
So hello, Mr. Ahmed, and I want to thank you for this overview session. I want to seize the opportunity and ask you about using ANN as a proxy in order to replicate the commercial physical simulators in reservoir simulation in order to minimize the time and computational resources needed for the reservoir simulation. So what do you think about it? And I want to specifically to ask you about, so I saw a lot, almost of papers and master theses that deals with that this methodology have very high accuracy, exceeds 99% in the test and training data. So is that high accuracy referred to a problem in the model? And what do you think in general about this methodology to replicate the physical simulator? Thank you.
Thank you, Mohammed. This is an excellent question. Yes, so machine learning, ANN, and actually other different machine learning tools can be used to build a proxy model. So it's the same as the stuff that we are dealing with. And the proxy model, you basically run your simulator for different simulation time, and then you teach or you learn your model. You ask your model, which is the ANN here in our case, to learn from this scenarios. So, for example, you have your model, it is porosity, it is 0.15, and your grids, your permeability is this value, and so on, so on, so. And based on this one here, your production rate, it was this trend, like it was increasing and then it started to decline after some times. Okay, so you ask your model to learn from this available data in order to predict the future performance. If you change the porosity to this value, how gonna be the trend look like? Okay, so still it is another one of the let's say regression problem. It's close to regression problem, where you gave it basically a certain input parameter and you ask it for an output, which is in this case here your output going to be the flow rate versus time, how it look like, or your pressure versus time. So this is your basically your proxy model. Your proxy model here, it's basically built on a certain cases that you already run on your simulator, and then you input this inputs or this scenarios to your machine learning model that it will learn from it. And once it learns from it, it will be able to predict the future trend. This is for regarding the first question. Your second question, the accuracy 0.99. To be honest, it depends on the problem. If your problem is simple, that can be solved with typical nonlinear regression model, the ANN is very strong tool. It will able to detect it very quick. As a result, your accuracy will be very, very high. Okay. Or if your data point actually was your input parameters like x1, x2, x3 was actually driven from a certain analytical equation. Like you used Archie equation to predict the water saturation as a function of the resistivity and the porosity and so on. And then you used these parameters later on to your ANN model. Okay, so your model ANN, basically input and output parameter, is basically the relationship. It is from the Archie equation. So the ANN model is a strong, very strong tool. It will be able to detect this relationship quickly with even very few neurons, and it will be able to get the relationship and have high accuracy. So the accuracy depends on the your problem. It has the complexity of the problem, how the input parameter you collected, the relationship between the input and the output, and so on and so on and so on. From the research point of view, if your accuracy is better than what you had, whatever published before for the same data set, that means you made an improvement. Or if there is no, this idea was not here before, like the prediction of the lithology, for example, from the drilling parameter was not here. So if you were able to get or predict the lithology with an accuracy like 0.9, okay, it is good, it's still innovative. This is from the research point of view. I hope this answers your question.
So very clear. Thanks for this professional answer for this question. So that's all the questions that we have in this session. So thanks, Mr. Ahmed, again for this valuable lecture. So anyone in the meeting, don't forget to fill the attendance form so to get the certificate of this course. Again, thanks, Mr. Ahmed.
Thank you. Assalamu alaikum.